Okay, L'Hopital's rule again, and let me. This is where we left off last week, and I know that this looks familiar to you. Okay, I know that you look. I know that this looks familiar to you. You have limit as x approaches a of f of x divided by the limit as x approaches a of f prime of x divided by g prime of x. But there are given conditions in here, and I want you to understand this. Okay, these really are the given conditions. This is what needs to happen. Given we really need to stipulate that the limit of f of x and g of x need to be approaching 0, or the limit as x approaches a of f of x and the limit as x approaches a of g of x equal plus or minus infinity. Yep. This creates the indeterminate form 0 over 0 or infinity over infinity. Can I show you a graphical representation very quickly? This is really the chief understanding that you have to think about in this scenario. If I have something that looks like this, okay, let's suppose that I have f of x is y equals x squared. And let's suppose I have another one that looks like this. G of x equals 1/2 x. Okay? If I have those two different functions, just look at kind of what happens here. If I were to take one divided by the other, namely if I were to go like this, the limit as x approaches, say, infinity, okay, of the top function, which is x squared divided by 1/2 x. And as you looked at that problem and you said, well, as what's this top function approaching as x approaches infinity? Infinity. What's the bottom function approaching? Infinity as well. They're both approaching infinity, so I have infinity over infinity. So in this situation, you could take the derivative. And the derivative is the rate of change, correct? So let's just look at this for a second. What is the rate of change of the line? The rate of change of the line is 1/2. The slope is always 1/2. How about the slope of this equation right here? 2x. It's going to be the derivative, and it will constantly get greater and greater and greater and greater. And so because of that, you can see in this situation that you have a constant slope. In this one, you have one that is changing. So the other day as we were talking, we looked at what happens in this situation. You have to, once you take the derivative, and we say the limit as x approaches infinity of, what's the derivative of the top? 2x. What's the derivative of the bottom? 1/2. And so as you do 2x divided by 1/2, you get 4x. But notice at that point, the limit of the bottom is not approaching infinity anymore. The limit of the bottom is not approaching 0. I have a defined number. And so when you have a defined value in the numerator and the denominator, you can no longer apply L'Hopital's rule. So for example, if we were to take the derivative of this again, that would not work out. So once you have something that's defined where you can plug in infinity, it's going to work out. And you say, well, I plug in infinity to the top, I get infinity. Yes, but the bottom, you have a constant value. So anytime you plug something in and you get a constant value, we have to cease from working with L'Hopital's rule. And in this situation, we can define it quite easily. 2x divided by 1/2 is 4x. As you let x go to infinity, where does this go? Infinity. And if you look at this, yes. If you were to take the values of the blue divided by the values of red, here they're very close. But as you move on out, you can tell that they're going to get much farther apart. We're going to approach infinity. Let's look at an example that we tried similar to the other day and see how it works out. Okay, so in this situation, we have the limit as x approaches 1 of natural log of x over 1 minus x. So the first thing that we have to do, and this is where we ran into confusion last time, is we first must test to see whether or not it's going to work out, whether we can even apply L'Hopital's rule. So let's watch what happens. As you plug in 1 here, you get 0 in the denominator. How about natural log of 1? Anybody know what the natural log of 1 is? That means e to what power is equal to 1? What power would you take something to get 1? 0. So we do get 0 in the top divided by 0 in the denominator. So in this situation, we can apply L'Hopital's rule because we have a 0 over 0 situation. That's what we have. So let's apply it. Limit as x approaches 1 of, what's the derivative of natural log of x? And what is the derivative of 1 minus x? Negative 1. I'm now just going to multiply by the reciprocal, and I get negative 1 over x. Can we plug in 1 at this point? We can. So we get negative 1. You need 0 over 0. We need 0 over 0. Okay, the limit as x approaches infinity of e to the x over x squared. E to the infinitieth power. What number am I going to approach? And x squared. So I now have a different form. Before I had 0 over 0. Now I have infinity over infinity. And so this is going to create a problem. So I can use L'Hopital's rule in order to try to get rid of this issue. And so I can take the derivative of the top divided by the derivative of the bottom. So namely, what is the derivative of e to the x? E to the x divided by 2x. Now I try to apply the rule. When you plug in infinity to the top, you get and to the bottom. So because I still have infinity over infinity, I can apply it again. But before, we were continuing to apply it even though we didn't get to those situations. So because I have that situation, I can apply it again. We have limit as x approaches infinity of e to the x over 2. So, what's e to the x to the infinitieth power? Infinity. And how about 2? That remains constant at 2. So, in this situation, you do not arrive. You do not arrive at a condition like we had before. You arrive to infinity over 2. So what we have to do is we have to look at our function right here. And this function, as you can see, is 1/2 e to the x. And if you would look at that graph, it simply just goes like this. Now it goes a little bit less of a rate than, say, just the generic e to the x, but it still does go to, as you guys can see, infinity. Well, you can look at the graph, knowledge that, any exponent to a positive, or I'm sorry, anything to a positive exponent is going to bring us to infinity in that situation. We're finding the limit of the function, so we're trying to deal with difficult limits. Difficult limits. Okay? Okay, this situation, we get natural log of x over the cubed root of x as x approaches infinity. And so for the natural log of x, if you were to look at that graph, it does look like this. It heads up very slowly, but it does approach infinity. And the cubed root of x, similarly, looks like this. So it's somewhat similar in terms of how it heads off, and it also does go to infinity. And as you look at the graphs, it's really not certain as we look at them what's going to happen. We're going to have to... Bonnie is doing up-downs in the hallway right now. Crazy man. Yes. Okay. He just got done. So I can apply L'Hopital's rule. I get the limit as x approaches infinity of 1 over x and then the cubed root of x. What's the derivative of x to the 1/3? Now, as you look at this, I'm going to rewrite this very quickly as 1 over x over 1 let's look at the top. If you plug in infinity to the top, what do you get? 0. You would get 0. And if you plug infinity into the bottom, what would you get? You would get 0. So notice that we went from a infinity over infinity to a 0 over 0 type. Now, you could try applying L'Hopital's rule again. But you're going to continue to come up with that situation over and over and over. And so, as you can see in this situation, what should we do instead? Multiply by the reciprocal. Thank you, Brady, for being the voice of reason. Limit as x approaches infinity of 1 over x times 3 cubed roots of x squared over 1. So this is like 3x to the 2/3 I will end up with 3 over x to the 1/3. Now, I can plug in infinity. Infinity to the 1/3 is still infinity. 3 divided by infinity will give me 0. Okay. Yeah. Yes. Two. What's that? Don't in this one. 2. Negative from the negative side. Now, I don't know if you guys necessarily know exactly what these graphs look like. But if I were to divide these up into pi and 2 pi, and I were to look at this graph, I'm going to first look at the graph of sine of x. This is the limit as x approaches pi from the negative, okay? And so if you look at this graph, sine of x looks something very similar to like that. That's what sine of x looks like. And 1 minus the cosine of x looks like this. It's going to start instead of starting at -1, it's going to start up here at 0. It's going to head like this. Yep. That's what those graphs look like. And so sometimes having knowledge of the graph really helps. But as you think about it here really quick, if I were to take the limit as x approaches pi from the negative of sine of x, as I approach pi from the negative, what value does sine of x approach? 0. Over, and then let's look at 1 minus cosine of x. As you approach pi from the negative, you approach 2. So in this situation, you may say to yourself, well, why don't I apply L'Hopital's rule? You can't apply L'Hopital's rule in this situation. Because as you have 0 on the top, you don't have 0 in the denominator. And you know what? That's actually helpful. If we simply just plug in that value of pi into both of these, as you can see, you end up with 0 over 2, which is just 0. So throughout your problems that you try, you're going to want to just take the derivative right away. But if you carefully look at it, as you can see, you don't need to take the derivative. If you plug in pi, sine of pi is 0. Cosine of pi is -1. So you get 1 minus -1 or 0 over 2, which is exactly what I showed you from the graph. So we can just plug in pi into the scenario and evaluate it. So sometimes you could plug in the values and you're going to get 0 over 0 or infinity over infinity. In this case, you just get 0 over 2 and you're done. One more example. Okay, the limit as x approaches 1 of 14x to the 5th minus 14 over 6x to the 4th minus 6. If you were to plug in 1, what would you get? Yep. Because we come up with what is referred to as an indeterminate form, something that we can't define, we'll apply L'Hopital's rule. And so you end up with the limit as x approaches 1 of, what's the derivative of 14x to the 5th minus 14? 70x to the 4th over. Now, here's where I want you guys to be careful. When you guys see this, so often you're going to think to yourself, well, it's going to be 0 on the top and 0 on the bottom because you're used to plugging in 0 or you're used to plugging infinity. What number am I plugging in? 1. And so as you now check each time, can I plug in 1 and get a defined value in the top and the bottom? I can. If I plug in 1, I get 70 over 24. If you were to continue to use L'Hopital's rule and take the derivative of the top and the bottom, it would not work anymore. You can only do it for indeterminate form, 0 over 0 or infinity over infinity. Because if you notice, Aaron and Ashley and Claire, we tried this the other day, didn't we? And we got 280 x to the 3rd over 72 x squared. And we worked it all the way down, but it no longer works. Okay. So, does that clarify any questions with L'Hopital's rule? Yeah. One second. Limit as of. Okay. So watch what happens here. Aaron's picked out a nice example. We have to start off by first plugging in 0. If you plug in 0 to the top, what are you going to get? 1 minus 1 is 0. Because any number to the 0 power is 1, and then we subtract 1 and we get 0. Now, if we plug 0 in the denominator, what are you going to get? 0. So L'Hopital's rule says, you know, we could do that. We can now take the derivative of the top and the bottom. Well, watch what happens, because this is an interesting scenario. If we take the limit as then t approaches 0 of, what's the derivative of e to the t minus 1? E to the t over, what's the bottom? 3t squared. Now I have to go through that process. Can I plug 0 into the top? What do you get? 1 divided by, what do you get in the denominator? 0. So this is not a situation where we can any longer apply L'Hopital's rule. We know what this is approaching. So because of that, we have to use some other type of understanding. Now, I want you guys to think about this for a second. We have the number 1, and we're dividing by, instead of 0, think about, let's say we're dividing by a really, really, really small number. Say like, yeah, if you take 1 and divide by a really, really small number, you get a really big number. And so as you evaluate this limit, you want to think about this. The limit as t approaches 0. I'm going to show you. As you look at this situation, you look at the limit as e to t approaches 0, and you know that that is going to 1, right? And if you look at that graph, e to the t over 3t squared, boys, please. At the bottom we have 3t squared. You can see that is approaching 0. If you actually look at the graphs, we have this 3t squared is this parabola going up. And then we have this e to the t, which looks like this. So you see how this graph is approaching 1 right here? And this graph is approaching 0? You're actually taking, this number dividing by this number, and we don't really come up with the determined value that you want. So if you actually look at this graph itself, y equals, if we go to e, well, I'm in parametric form. I'm sorry, I was in parametric form last hour. There we go. I want a function. Look at your graph. You see what's happening to your graph? As I type in this graph to my calculator, again, we're taking a large number divided by a very small number, and so it seems like it would go towards infinity. As you actually check this graph here and we analyze it graphically, you could even check your table if you want to, and you could plug in a number really close to 0, say 0.1, and see what you get. Oh, ass. There we go. So if you go into your table set and we punch in, say, 0.1, you could tell that you get 36.001 and you get 330. You could tell that you're going to what value. So this is an example right here that when you run to this point, you understand you cannot apply L'Hopital's rule. You have to really do two things. Either A, algebraically, which cannot be done, or B, analyze through graphing, which is what we did. You cannot do it algebraically. That's a discussion for calculus 2.